I'm Roy Shadman. I'm one of the team members at AnyLog. Before we get started, I'll read the LF antitrust policy notice. So the Linux Foundation meetings involve participation by industry competitors, and it is the intention of the Linux Foundation to conduct all of its activities in accordance with applicable antitrust and competition laws. It is therefore extremely important that attendees adhere to meeting agendas and be aware of and not participate in any activities that are prohibited under applicable US state, federal, or foreign antitrust and competition laws. Examples can be found at this link. I'll let everyone else read the second paragraph. And if you are curious about what the policies are, please go to this link. So I'll leave it up for a second. So today's talk, we're very excited to present this talk. It's titled EdgeLake AKAVE FILECOIN, End-to-End Edge Data Management Without the Cloud. And we're going to present some very cool and new solutions that we are building. And we also have a representative from AKAVE here, Craig, who's on the call. And we'll have a Q&A session to have a deeper discussion. So the agenda will be, I'll talk about the data flow of the edge today, or traditional data flow. Then I'll go into today's edge. I'll talk about the edge data fabric, which is EdgeLake's solution to the problems. And then I'll do a live demo and we'll conclude with a Q&A and discussion. So today's edge is composed of a bunch of an edge environment where you can have ships and vehicles and smart cities. And all of these components are connected to edge devices, but that's where the edge ends. Today's edge is just where the edge is, and everything moves to a data center that is often very far from the edge environment. So what we end up doing today is we end up sending all the data to a data center, and this data includes video, file, JSON data, CSV, machine learning models. Everything that is done at the edge goes to the cloud, and we do the computation in the data center. And then all the decisions, the analytics, the file data that we need, the ML models, all the control decisions come back to the edge. And this is a very inefficient and expensive process. And so we can summarize the current problems at the edge is that we have a distributed data network. The edge is very distributed with very different number of components, but we don't have a unified view of this data to make the control decisions and make the decisions that are important. So everything has to go to the cloud. And the reason is we don't have there's no centralization. There's no unified view, and centralization is required. And then on top of that, we also want to start integrating AI at the edge. And this requires to have some sort of object storage to manage the machine learning models and be able to update those models and inference endpoints. But this is also really complicated because the edge often has some resource constraints. And the bigger the models are and the more advanced they become, then we're going to start seeing some data growth limitations. How are we we don't want to overwhelm those critical processes with managing all this object storage. On top of that, there's also significant cost with the current pipeline, and specifically with ingress and egress costs. And this cost is proportional to the consumption of the data that we're using that's going to the data center, and also how valuable this data is. And the more valuable the data is that we send to the data center, that means we have to pull that data back to the edge at some point. And then we're also seeing scalability issues. And the only way we can scale the edge is based on how much we can ingest data to the data center, process that data, and then send all the data or whatever the results are back to the edge. So this is there's a limitation here on the network as well. And so on the technical sides, these edge nodes are composed of proprietary software, and they're built on legacy systems. And so we have each company is essentially building their own system and their own solution. And when an engineer on that team leaves, there's a lot of sunken cost in having to rebuild the proprietary software. Again, these edge nodes have to do massive data transfers to the cloud or to the data center, which means that you lose your data ownership. So once you give the data to the cloud, they become partners in your data, and their incentive is to have you service the data back to the edge where where you want to operate. And then obviously, once you go to the cloud, you don't have any real time anymore. So all your analytics are going to be stale. And to compound all these negative effects, it's also quite expensive to send the data to the data center and operate in the data center, because you not just have to send the data to the data center, you also have to start paying for data services like Postgres and databases and file storage like S3 buckets. All these things compound into a very expensive solution. And then in the worst case as well, you don't have real-time actuation at the edge, because all the decisions are computed at the data center and have to come back to the edge. So that's a quick summary. And I'm happy to say that we believe the time for change has arrived. And we, with EdgeLake, are building the Edge Data Fabric, where your edge devices, so your cameras, your charging stations, your oil rigs, they send data to an EdgeLake node. And this EdgeLake node is composed of data services. For example, AKAVE and FileCoin for object storage. You can enable SQL services for like Postgres for database management solution, or you can enable Kafka to pipe data from one place to another. But what the key important part is that all of these services are enabled via a virtualized Edge Data Fabric enabled by EdgeLake. So when applications don't need to know where the database is, they don't need to know where the object is. All they need to do is send a request to the Edge Data Fabric, and EdgeLake will execute the query and return the result back to the application. And this is all, so we essentially are simplifying the entire management of all your data services at the edge. All you need to do is send the data to the Edge Data Fabric, and EdgeLake will return you a unified result of all your data, no matter where it is and no matter the distribution. So for people who are new or watching this video, so what is EdgeLake? EdgeLake is a plug-and-play software solution. It's the core component is EdgeLake Core, which sits on top of the operating system. And you can deploy EdgeLake Core using solutions like Docker, Kubernetes, IBM Open Horizon, Dell Native Edge. All these solutions support EdgeLake Core. And once you have EdgeLake Core, you can start enabling services like database services, PubSub services, blob storage services. And all these services are essentially abstracted to appear like all the nodes. So all your EdgeLake cluster appears as if it's one physical machine. So you don't need to know where your data is. EdgeLake or the Edge Data Fabric finds where your data is and returns a unified result very efficiently. Example services that we have, we support northbound connectors like REST and SQL. We have rule engines. You can dynamically manage schemas and data storage and collect data with MQTT, PubSub, OPC UA, and so forth. And so the key talk of today is we've integrated into AKAVE and FileCoin. And so this is an object storage solution, and I'll talk about why this is a key enhancement to EdgeLake Core. And specifically, our current approach to store objects was that we store all the objects on the local file system of each EdgeLake node. And this created a couple challenges, is that these EdgeLake nodes are usually running critical processes. So all the real-time analytics are going to these EdgeLake nodes. But once we have these objects that contain machine learning models or copies of data, then the storage rapidly gets exhausted on the EdgeLake nodes. And so we don't want to impact the critical services of EdgeLake. And obviously we don't want to risk any essential real-time services that EdgeLake is powering. And so one of the things is we don't necessarily need those objects on EdgeLake itself. We just want EdgeLake to have access to those files in a very efficient way. And so what we need is an edge native object storage solution where we don't have to send the objects to the cloud. We can keep them at the edge and we can access them when we need to. And this is particularly useful for video files where videos are of massive size, or machine learning models where they could be at multiple gigabytes alone. So we want to minimize the ingress egress to the cloud. So this is where Akave comes in. So Akave, we can deploy Akave anywhere. And Akave can be hosted on local servers or on premium data centers. So you can manage your own Akave environment, or you can offload that to some data center of your choice. And the key point with Akave is that it allows us to support data sovereignty and ensures regulatory compliance. And so the key difference between Akave and a solution like Amazon is, one, you can deploy Akave at your edge, but also you can control exactly where your data goes. You don't necessarily have to trust that Amazon is keeping where Amazon is keeping it. You can define explicitly rules that my data goes to this specific environment. And with all of this combined, this is the Edge data fabric. So notice now that we have our Edge ecosystem, and this Edge ecosystem is empowered with EdgeLake. So all the data is going to EdgeLake, and EdgeLake is now the interface to pushing the data to Akave. So you can define rules in EdgeLake and say, I want to offload all my video files to this Akave service. And Akave here will manage all the objects for you dynamically. And when you want the object back at the edge or back to EdgeLake, all you do is you send a request to EdgeLake. EdgeLake sends the request to Akave, and the data comes back to EdgeLake, all at the cloud, all on your edge network. And you might be asking, where does Filecoin come in? So Filecoin is the archival storage. Filecoin is when you don't necessarily need the data at the edge anymore, and you want a cheaper solution to manage this data. And so through Akave, you can offload your data to Filecoin via archival storage. And this is equivalent to AWS Glacier solution. So Filecoin is the AWS Glacier, and Akave is quite similar to your S3 in AWS. And so with this Edge data fabric, you get an end-to-end lifecycle solution. So your distributed data network now has a unified data view with EdgeLake. There are no central dependencies. EdgeLake is resilient to a failure of an EdgeLake node because the system is highly distributed, and there's availability you can add on top of your EdgeLake cluster. You can set up object storage anywhere and at any scale. So you can dynamically provision more Akave instances at your edge to manage all your object storage, just like you can deploy more EdgeLake nodes to manage more data in a database or in other data services. Your ingress and egress costs are also fixed. Because you're only operating at the edge and within your network, you don't have to pay the ingress and egress costs. So that's a significant cost reduction. And the scalability now becomes horizontal. You just plug in more machines, plug in the plug and play software, more EdgeLake instances, and you can scale horizontally now. So I'll transition now to what we are going to demo. So we have an Acme retail site, and we have an Acme store, and this store is producing video files video data. And this video data is going to EdgeLake node. And so this entire infrastructure is powered by the blockchain. And what we do is we keep references of where data locations and where operator nodes are. So operator nodes are nodes that keep the data. And so this entire setup is composed of Postgres, where we keep track of the customer's information. So for example, the department count, so how many, the department counts, the timestamp of the videos being ingested into EdgeLake, the department name, the video ID, the number of people that an ML model and added inference onto the video. And then we also, rather than storing the data directly rather on EdgeLake, we now store the data on Akave. And Akave offloads that data with based on retention policies to Filecoin. And another alternative that we're going to show is also MongoDB. You can also offload your data to a MongoDB node as well. But with this data platform, you can now have an operator node that defines that they are part of the Acme company of the San Francisco branch, and that the department is kitchenware. And they will start pushing data every time they receive videos. They will start pushing data into a SQL database, and then we can start running queries against the inference that happened on those data, on the data. And you can also run queries on the blob storage. And you can do all of this with EdgeLake native commands. So the basic configuration, as I'm showing you I'm showing you the commands. This is fully automated within your deployment. But essentially, all you need to do is you need to assign a SQL DBMS. So you just initiate the command connect DBMS customers, which is the logical name of the database that you're initializing. And you're specifying the type is Postgres, so pSQL. And you're specifying that your user is AnyLog in this case, and then the IP port, password, or whatever the credentials are to connect to the Postgres instance. And then on top of that, you also need to define the where the blobs are going to. So you do the same approach. So connect DBMS customers where type equals Mongo, which signals that the video files are going to a Mongo DB database. And you also provide the parameters or the credentials of that instance. On top of that, Mongo and AKAVE are completely interchangeable within EdgeLake. So you can also do this by connecting to a provider in AKAVE. And you can do the same thing with bucket provider connect, where group equals branch videos, and provider equals AKAVE, and then your AKAVE credentials as well. And once you do that, you just need to define that your DBMS is customers, the type is bucket, and then your connection is the logical database connection called branch videos. And that's all you need to do to set up a connector to AKAVE or the one-liner to Mongo. So the automated data flow is as such. So we have a camera, and this camera is generating video data, which is being sent to an AnyLog node. The AnyLog node sends so there's ML models running on AnyLog or nearby on an endpoint. The inference on this video, so the ML inference, goes to a Postgres database, so we can query this data. And the physical file goes into an object storage solution like AKAVE or MongoDB. And now when you run a SQL query against your data, you can get information about the inference that was done on the videos and the video itself. And I'll show that in the demo. And that's in the next step. And all of this is abstracted to you. So you don't need to know if your data is in AKAVE or if your video is in Mongo. You just send the data to just like a SQL query, and we return to you both the video and the inference results. So how does the query work? So we have a blockchain with a bunch of policies, and these policies contain ontology of data location, who my operators are. So each operator here would have a policy. What data does each operator store and manage, and so forth. And when I have a query, I send the query to any operator node or any query node in my network. It doesn't matter which one. Each node is a gateway to the data. So they're completely equal in those sense. So when I issue this query, that node that receives the query becomes the data gateway, and it does a lookup on the blockchain policies of what are the other nodes that have the data relevant to my query. So the blockchain will tell that node that these two nodes that are pointed out have the relevant data to my query. And so it'll issue the request to these nodes, and then the nodes will return a result set to the gateway node, and the gateway node will return a unified result to the user or application. And that's all it is. So I'll transition now to a demo to kind of show this, and I'll go a step-by-step setup. So bear with me for a second. Before we go to the demo, is there any questions?
Could you say that one part about, it was like 2 slides ago, on the inference
This?
where the video goes and then where the inference goes. Yeah, this one.
Yeah. So you have a camera. The camera's generating video data, and let's say you have a like an inference endpoint sitting on AnyLog or somewhere, right? So the video comes into AnyLog. If you set up an inference endpoint, you're creating more data. So you're creating that there are two people in the video, right? Something like that, right?
Oh, okay, okay.
So that inference result can get sent to Postgres. And then, but along with that inference result, we're also mapping what video resulted in this inference result. So when you want to say issue a query, give me all the videos, or give me all the inference results that had two people in the video. You issue that query to EdgeLake, and you not only get all the a list of videos that tell you these are the inference results, but you also have access to view the data, the video files from one place. You don't have to know that my object is stored in AKAVE or the object is stored in a MongoDB instance. The inference could be stored on one node and the object could be stored on another node, and AnyLog abstracts the entire query process for you. So when you issue that query, your interface is like the entire data network, or your entire EdgeLake network is a single unified machine. But really that data is highly distributed on multiple nodes.
Thank you. Yeah, that part had always tripped me up in the past because I had always been thinking about, is the camera, I was thinking that the camera was somehow doing the inference, and I was like, how is how are we gonna deploy
Yeah,
that?
yeah. I guess if you wanted to, you could put another server on the camera with like a GPU or some inference endpoint and
Like
route the
it,
video and the inference directly. But I think most of the time the camera would be sending the data to AnyLog, and AnyLog would either push the inference to another EdgeLake operator or another EdgeLake node that is managing an inference endpoint, or just inference directly
yeah.
on the device.
They have
But then all this metadata is stored in Postgres, and your view of both the object and the inference results is unified. So the object is going to be stored on a different node, and the inference is stored on another node. But when you issue that query, you get both without having to know where your data is.
seamless.
So does that answer your question?
Yeah, completely.
Okay,
They
cool.
have these new what is it? So SoC chips that are the Google Coral TPUs. They've got two TPUs, and it's on a tiny little chip. It's pretty cool.
Mm-hmm.
You can do
Yeah,
all the computer vision and everything.
yeah. Okay, so I'll now do the demo. So what I'll simulate here is I'll simulate two EdgeLake operators, a master node and a query node. I'll go over each one as we use them. But what I'll show first is that my Docker environment is empty, and we'll first start by
Sorry to
deploying.
interrupt. Can you make the windows bigger? It's really hard to
Yes, yeah.
read.
Thank you for the reminder. I forgot about that one. Another thing that I'm gonna apologize in advance for is we had some issues with our Akave keys yesterday as we were preparing the demo. So we're gonna show the demo today with a MongoDB with two MongoDB instances. But I want to just make it explicitly clear, as I showed in the slides, that they're completely interchangeable. They're they're replaceable solutions. So you can either choose to deploy on a Mongo or a Kave. And so we'll have another demo next week. We're presenting this collaboration and integration again at IBM Tech Exchange 2025 in Orlando. And we'll have another demo, and I think it will be recorded. So we'll make sure to share that recording with the LF Edge community as well. So the first step is
Roy, sorry, just one comment to make it clear. Maybe you could tell the use case that we're trying to simulate a retail store, 2 departments, different locations. So, yeah.
Yeah. So essentially what we're trying to simulate is we have retail stores we're going to simulate 2. So one in San Francisco and one in New York. Both of these stores have cameras. And the aim of these cameras is to run inference and predictions on how many people are in the store. So we'll essentially deploy our EdgeLake operators, a master node and a query node. And then we'll start inserting data to both EdgeLake operators. So we'll insert data to the San Francisco location and one to the New York location. And then we'll run a query, and I'll show you how you can, from a single point, view all your data without having to know whether the data is in San Francisco or in New York. So we're going to completely automate and make this entire view of your data completely unified and seamless. So I'll deploy the Postgres containers first. So if we hopefully this is big enough. I'll make it a little bigger. So we can see on Docker PS, we have 2 containers, Postgres 1 and Postgres 2. So we're going to slowly build this up. So we're also going to spawn up 2 Mongo containers. So again, if we start looking at our Docker setup, we have 2 Postgres containers, 2 Mongo containers. Each container is completely independent, running on its own port. So Postgres 1 is on 5432, while Postgres 2 is on 5433 port. And then Mongo is on 27017 for Mongo 1 and 27018 for Mongo 2. So these are completely different, completely simulating a distributed system and just in a distributed edge environment. So now that we have our databases set up, we are now going to deploy our AnyLog cluster. So I'll do it one by one. So the first step is to deploy your master node. So if we look now at our Docker environment, or let's do it down here. So if we look at, we now have a master node here, and this is operating on port 32048 and 32049. And so if we attach to it, we can see that our network is composed of only 1 node. So we have 1 master node, and it's currently connected to itself. And so now we want to start deploying more nodes. So let's deploy 2 operator nodes. So we'll deploy operator 1 here and operator 2. And again, if we look at our Docker environment, we went from just having a master node to having an operator 1 and operator 2, each operating on its own port or set of ports. And so if we want to attach to operator 1, we can start about running some like a test network command. So we can see if our cluster is connected to each other or not. And we can see now that we have a master node, an operator 1 and an operator 2, and they're all connected. And if we look at the databases our operator 1 node is connected to, so remember I had spawned a Postgres container and a Mongo container for it. So if you run get databases, and let me make this a little cleaner. So we can see that we have a MongoDB database called blobs customer. And we also have a database called customers. That's a Postgres table or a Postgres database. And this is very similar to what I was showing here, where we defined our blob platform. And we also defined our Postgres table that's going to keep track of the inference done on the video data streaming into the EdgeLake node. So So the next step is we also want to deploy a query node. The difference between a query node and an operator node is an operator node is a node that consumes data and manages data. A query node is a gateway to the data. An operator node is also a query node, but we like to separate that responsibility to a query node on its own. So let's deploy the query node. And if we look at Docker again, we now have a operator node, two operator nodes, a master node, a remote CLI, which is the web GUI that we use to interact with the network. I'll show that in a second. And we also have a AnyLog query node as well. So if we reattach to the operator node, we can run the test network command, which evaluates all the connections within the network. And so we can see our network is composed of 4 nodes, a query node, 2 operator nodes, and a master. And the plus sign signifies that the connections are, that the nodes are able to connect to each other and synchronize with each other. So I'll show some commands now just so people get familiar and see how EdgeLake operates. So if we do blockchain get star, these are all the policies that are used to define the EdgeLake network. So for example, we define a config. So we defined our master node configuration, what the node type is, what the company name is, what port does it operate on. So this is a port that's defined via variable. So you can also print these variables to each other. So it's not being hard coded. These are all dynamic configurations based on my deployments. And so we can see that we have a configuration for a master node. We have a master node defined here. So we can see that the master node is operating on the IP 172.168.0.2 on port 32048, and then also on a REST port 32049. And then the node's location, which is automatically generated by EdgeLake. So I'm currently in San Carlos, as you can all see. So we have schedules these are generic scheduling policies that are created with your deployment. We have another operator config here. So this is for the operator nodes are using this configuration deployment. And then each operator is defined with a cluster. So a cluster essentially is where you can enable your high availability. So if you wanted to replicate your operator, so you wanted to have high availability on your data, you would deploy another EdgeLake operator with the cluster name SF branch. And if you wanted to replicate your New York data, you would deploy another operator node with the cluster NYC branch. And anytime the EdgeLake operator, the primary node, gets data, it'll forward that data to your backup node. And so that's how we ensure high availability between the nodes as well. So yeah, so that's basically the gist of the policies. Mark, is there anything else to point out, or Moshe?
No, I think you got it.
Okay, so I'll do another, we'll attach to the second operator node so we can see some things. One more thing that I'll add is you can also, one of the nice things about this abstraction where you don't have to, between EdgeLake's abstraction of operator nodes and entire distributed environment, is that you can actually run queries from any node on any node. So I can connect to the node on the left here, and I can run queries directly on it. So if I do run client here, I can run like get status, and it'll return me the status of the operator 2 node. So this node is the one on the left here, and I can run commands on it as well. So you can kind of through one node is your gateway to your entire network, and that's what I'm trying to show here. But nevertheless, if you want to go back to the main node that you're running on, now I'm running on operator 1, and so if I do get status, I'll see the status of operator 1, not operator 2. So okay, So now for the setup, we want to start defining what data these operator nodes are going to take in. So we have a script here that defines data called blobs people videos, and we deploy them on both of these nodes. But what this does is that it creates a policy called mapping. And this policy defines that there's a topic called people videos on a database management that is defined within when the data is inserted into EdgeLake. And then we define the schema of the data that the EdgeLake operator is going to receive. So the schema is going to include a timestamp, a start time, an end time, the file itself. This is the inference, is the number of people in the video. And then what is the confidence of the ML inference that determined that there are 1, 2, 0, 3 people in the video. So we're defining our data. So now we can start sending data to both operators. And so we're starting our data generation script. So we can see that we're in round robin sending data to each operator node. And if we wanted to, we could do get streaming, and we can see that operator 1 received 7 files so far. And I could go on operator 2, but I also could just from operator run connect to operator 2 and run the same command and see that operator 2 received 12 files while we've been waiting. And so I can manage every node from one point, which is a really nice feature. So now that we have data coming in, we can go to the AnyLog remote CLI, which is our GUI. And this GUI is very similar to Postman. It allows us to send REST requests. And so let's start with sending a query on the data. So what I'm going to send a query on is I want to return the branch, the department, the IP port. Let me make this bigger for everyone. I want to select the branch, the department. The plus means that this is provided in the query. The at means that this will be generated by the SQL results. But I want to return these columns in the format of JSON. I want to move the timestamps into UTC timestamp. And here's my select statement. So I want to select the file, the start time, the end time, the people count, which is the machine learning model, the inference, the confidence of the prediction or the inference on the file, and then from the table, people counter. And then where timestamp is from 3 days ago, etc. So I'm issuing this query, and I'm sending this query to my query node. So the query node is going to act as the gateway to the network. And I'm going to signal that I don't know where my data is. If I knew where my data is, I could just send this query directly to a set of nodes. So I could start putting IP addresses and ports here, but I don't know where my data is. So I'm just telling the query node that I want to execute this SQL query and I don't know where the data is. So I'm going to send it to the network and you find me the data. So if I send this query, then I get a set of results with the branch name, the department, the IP, the port of where the data is coming from, the DBMS name, the table name, and the file name, etc. So I'll point this out just so it's addressed. So you'll see some duplicates here. We only have 10 files in our in our data generation. So it's repeating the files, but nevertheless, the data is going in and we're running inference on this data. So for example, on this file, there are 0 people predicted with a confidence of 0.5, or so 50%, whereas in the video here, there's 2 people predicted and it's sorted by that. So let's select some files. So we'll select this one, which has 3 people, and this is a file stored in the SF branch. And we also want to select a file maybe from the New York branch. So let's do maybe one with 4 people in it. And so we'll select this one. So essentially we're selecting what videos do I want to view. And we go to the top here and we hit blobs. And now from a single point, I'm going to be able to see both the video files that I selected. And those video files were stored on a different a different node. So we can see that one video file is on a node with this IP address ending with 3. And then the second file that I selected is from a node ending with an IP of 4. So if we select them and we hit watch, so the videos will now be displayed, and we have a unified view of these video files. And we have it from a single point. I didn't need to know where the videos are. I just told the query node I want to get this specific file with this inference, and I want to get this specific file with this inference. The node found me the file and brought it to me to a single point. And it's a fully automated, seamless operation. There's no hard coding or anything. Everything is fully automated by EdgeLake, and EdgeLake, through the Edge Data Fabric, is facilitating all your queries and returning a unified result set, even though the data is highly distributed and you don't necessarily know where your data is in your data network. So that's the demo. I'll stop here if there's any questions. Jonathan, if you're on mute, maybe.
Maybe. Which node is the network client on?
The network client is connected to the query node.
Query node.
So if you want to see here, our query node is operating on 3248 and 3249. So 3248 is the TCP, so that's the inter-network IP port. So when the query node communicates with the operator node, it's communicating on port 32348. But when I'm issuing a REST request to it from a GUI that's running on my local host, then I issue the request on port 32349, which is the REST port. And if you wanted to, these are customizable. So if you wanted to know what the ports are, you can run get connections on the CLI, and you'll see a TCP and REST. So on TCP, I'm running on 32148 for operator 1, and my REST is 32149.
And are those, I was just pulling up the EdgeLake documentation. Are those commands all listed in the documentation, and
yeah,
like those SQL commands that you were putting into the network client?
This is a standard like EdgeLake query. So this is tailored for the demo. The SQL should be documented pretty thoroughly in the documentation though.
Okay.
If you wanted to replicate this, we can sync offline, and I can give you the data and the query. So
yeah.
So you can also simulate it. So just, are you on EdgeLake Slack?
Yeah, I just got my Slack back actually, so.
Okay, yeah, so sync with me and I can share with you the things to replicate this demo. For AKAVE, though, maybe someone from AKAVE wants to jump on, but those will need AKAVE keys. So you'll need, AKAVE's interface is essentially a replica of AWS S3. So any buckets, and probably MinIO as well. So any API that is using Bodo 3 in Python will work based on your access key, and your secret key will work on AKAVE, it'll work on S3. And if MinIO also uses that same library, then it'll also work on MinIO as well. It's one unified interface that we built.
Nice. From AKAVE here, just confirming that that's true. Yeah, we're compatible with MinIO as well.
Yeah, no, nice.
There are a lot of advantages to AKAVE. Bart, do you wanna do a little short plug on the advantages? I can give you the slide that I held back. I didn't know if you were joining or not, but there's this slide that I can share if this is helpful for you or not.
Yeah, totally. Thanks for pulling that up. I think you covered a lot of what makes sense in this context. We distribute the nodes, it's at the edge, but really the big thing that differentiates AKAVE from other decentralized storage solutions is what you sort of just mentioned there, which is the compatibility as an S3 compatible interface. So it works out of the box with a lot of AWS S3 tooling. We have a whole solutions section in our docs that's continually expanding if you do want to see like some of the ones that we specifically documented, but MinIO is one of the S3 CLI, Boto 3, things like rclone, Snowflake, Cloud Mounter, DuckDB, and because of the decentralized nature of it, we have that distributed node, distributed data. It's fully sovereign and it's your data, your keys. And we also have that additional layer on Filecoin. So I thought you actually did a great job covering that.
Where
Beautiful.
can you put Akave? Like
So
like
yeah, that was here. So you can, so Bart, maybe do you want to go or do you want me to?
What were you gonna say?
So Akave can either go, you can either self-manage your Akave instances. So you can host machines at the edge, deploy Akave and connect Akave to your EdgeLake network, or you can also deploy, I think Akave has their own cloud where you can, or they use data centers to provide a service for it as well.
so the source of my question is sort of, could you put Akave on like an Android?
It wouldn't work on an Android. There's going to be minimum hardware requirements. We haven't quite defined those yet, but the idea is to, yeah, distribute these across, starting with enterprise grade data centers, to make sure that the performance and scalability is there over time. But for example, the gateway, the S3 compatible API, what we call O3 gateway, is the next release will be self-hosted. That's like the next development target we have. So you could run that as a Docker container. It should be fairly lightweight. And then the node infrastructure itself, you can run, again, that's to be defined, but it'll be a little bit more heavy duty than something like an Android phone. But any kind of server infrastructure should be relatively compatible with it. The idea is to simplify it and to spread it across networks. So we have other DePIN providers that we talk to and that we partner with who are interested in running these Akave nodes alongside their own infrastructure. So there's a lot of different benefits to distributing it here, like Roy has already mentioned, but it's going to be the goal is for interoperability and the lightweight deployment. So maybe that answers the question, but
Yeah, that's cool.
Mhm.
Is it
It,
how does it distribute across like nodes on your own network? Is it
Yeah,
like, yeah, redundant
I said,
across?
yeah, so we actually use erasure coding. So in our docs, there's a section too. I just sent the solutions and integrations section in our docs, so you could see some of the ones that have been documented so far. But in addition to that, we have this section I'll shoot in the chat here as well about erasure coding, which describes how we do this. And essentially yeah, it's a little bit here. You can see it's split in data into different chunk sizes, and then those chunks get uh, encrypted and split across the network with a 1616 schema. And then it's done in such a way that the data is recoverable from just a portion of that. So it's like detailed in the documents that I sent there, but essentially it gets chunked into little pieces, it gets distributed across the network, encrypted, and it's recoverable from just a fraction of those.
But it's almost like it's like striped across, like not really striped, but conceptually sort of striped across a whole bunch of nodes.
Yeah,
Like
it's like split
RAID.
across a bunch of nodes, and there's parity, and there's the erasure coding allows you to have like some like up to 50% data loss, for example, instead of doing like a direct replication, for example, where if you just duplicate the data in two sources, if one of those is corrupted or fails in some way, then one copy is completely gone. We do the erasure coding so that you could lose up to 50% of the random pieces of those nodes, but still be able to recover the whole data from the remaining piece. So it's much more durable that way, and then it's also not a single point of failure. It's distributed across the network so that if one node fails, for example, or if one location or group of nodes fails, it's still recoverable because it's decentralized, distributed, and split off into pieces like that.
Oh, that's really cool.
Mhm.
And we also have Tim here from Filecoin. Tim, do you want to say anything?
Sorry, nothing to add currently, but yeah, just listening and great work so
Okay,
far.
thank you. Thank you for coming, Tim. So yeah, so are there other questions? John, go ahead.
Yeah, just quickly, this is John Reynolds. In the example we just gave, where you had the different nodes configured here, what was the role of the master node in that?
Right. So the master node, yeah. The master node is the orchestrator of the policies. So the nodes synchronize with the master node, but the master node can also be replaced with the blockchain. So right now we're using it as an emulator for the blockchain, but you don't necessarily need a deployment with the master node if you deploy your policies on the blockchain.
And if we're doing this, it essentially provides one role is a pointer, if you will, to be able to locate where the data actually is.
Yeah, so the blockchain is the one. So when I do blockchain get star, when a node wants to let's go for an example here. So when an operator joins the network, it tells the master node, hey, I'm joining the network. Here's my certificate. So the master node can authenticate that this node actually has permissions to join the network. And so it sends all this metadata to the master node. And once the master node approves based on the certificate, this operator node, it adds it to the ledger. And then when all the nodes, so all the other nodes, they will periodically go to the master and ask, are there any new policies? Are there any new policies? And the master node will return the new policies that the nodes didn't have. This can be replaced. So we also support like using the master node on a smart contract. And a smart contract is a programmable piece of code that works on a blockchain like Ethereum. And you can manage all your policies on the smart contract as well.
Got it. Okay, thank you.
Yeah.